And screen share. Oops, why does it do that these days? Okay, there we are. Okay, so I'm doing technical things today. My favorite, maybe. It's okay. It's all just different, you know, just doing what's appropriate for the given thing to do. So today we are doing details, all the details. Okay. So yes, what we're trying to prove. Let's just keep our eyes on the prize. We're varying. We're on a constant negative curvature surface. Let's have the word surface up here because that's really important. And we're varying through the negative curvature metrics on that surface, seeing how the entropy changes, you know, with respect to the Liouville measure. So all of these things are orbit equivalent, right? There's like a one-to-one correspondence between the geodesics. You know, the geodesics are kind of controlled by the topology, but you know, they're all, you know, if you think about changing the metric, you know, the actual flow lines are kind of changing a bit, and of course the speed is changing. And so although they're orbit equivalent, of course the entropy changes, and this amazing result is that the entropy is maximized at constant negative curvature, and only maximized at constant negative curvature. That's why it's a rigidity result. Yeah, this number, this very crude number, can tell when you're at constant negative curvature or not. Once we set everything up, if we can prove this expression here, so we got two conformally equivalent metrics, both with negative curvature. So this is the topological entropy, but I'm thinking about it as growth rate of periodic orbits or closed geodesics. To prove this inequality, we saw the argument last time to get this result. So everything hinges on proving this inequality. So let's do it. Okay, so we started last time. I've got a set A epsilon t. Okay, so remember that this bracket operation, it has a name, conformal coefficient or something. Yeah, okay. I don't know. I'm not going to give it a name. I think this has been named at some point. But what it's doing is it's measuring G2 length with respect to G1. So it's a number that's somehow comparing average lengths between these two metrics. And just using the ergodic theorem on this observable, just, you know, taking the norm of a vector in G2, and the ergodic theorem, of course, for almost every point, almost every V, the time averages are going to this guy, converging to this guy, in other words, converging to bracket G1, G2. So, so therefore, you know, if we allow ourselves an epsilon, you know, we can get an almost full measure set on which these time averages of this quantity are close to this thing, okay? And where am I at? All right. I'm now going to define a set B epsilon t, which is going to be the set of V into SG1M, so the unit tangent bundle with respect to G1. And this is going to basically have some kind of recurrence property. So property A, property given by the set A, is about vectors which are capturing this, seeing typical behavior for this thing, if we average. And the other ingredient is going to be things with a nice recurrence property. So that this is going to become quite Bergelsonian for a moment. Okay, so there exists a T with in the window t up to 1 plus epsilon times t, such that the distance, just be careful, in G1 V to ft G1V is less than epsilon. Okay, so it's just like a recurrence set. So obviously just Poincare recurrence for an ergodic measure. You know, there's going to be a full measure set, so things come back to themselves. This is very general, but I'm just getting something a little bit stronger. I'm saying that well, I'm looking for points such that there's a time in this window. So a big T up to, you know, a multiplicative factor times the big T, such that you get this recurrence back to itself. Okay. And just some notation. I like descriptive notation, even if this is getting a little messy. I'm going to write b epsilon greater than or equal to t0, that's all in the subscript, to be the intersection from t equals t0 to infinity, b epsilon t. So this is going to be the set of points such that for all times bigger than t0, you're going to have recurrence in that window from t up to 1 plus epsilon t. And the claim is that mu sub L G1 b epsilon t goes to 1 as t goes to infinity. Okay, so this set approaches being full measure. And once we've done that, I mean, why don't I just kind of show you where this is going. So what I want to do soon is find a set of positive measures, say measure 1/2, which is like this set intersect this set, suitable epsilon and t, so the thing has definite positive measure. And I'm going to end up with lots of points which have two properties together. One is that their averages are capturing this number, and the other property is that they almost recur back to themselves. Can anyone guess what will be good about these things almost recurring back to themselves? I'm searching for an obvious answer.
They'll form a set of full measure?
Almost. I mean, we're looking for a positive measure, but why is this property going to be useful for us? Can anyone guess ahead? Remember, we're doing periodic orbits here, right? So we're going to close them up. Sorry, probably wasn't a terribly fair question. I was just wondering if anyone would guess where I was going. So we're going to use this property to close these things up to closed geodesics. So we're going to build lots of closed geodesics which capture this number along their average. Okay. And there's going to be lots of them. So maybe we can start seeing where this is going. There's going to be lots of them. Hopefully that's going to capture something like this. We're going to be seeing average behavior like this. Hopefully that number's coming out there, but they're all going to be closed up into closed geodesics, which is hopefully going to give us something with that number. Yeah. Okay. All right. So I wrote something down to see this. That wasn't obvious to me at all. This is an exercise in kind of very general ergodic theory. I'm going to take a finite partition. So I'm improving the claim here of SG1M into sets of diameter less than epsilon. Let's see, be a partition element by ergodicity. So the ergodicity, which we got from the Hopf argument, is again absolutely key. There exists a set Z with full measure. So for all V belonging to Z, the limit of 1 over T St chi of V equals, hang on, what do I want to write? Equals, the measure of C, right? Where St phi is going to be the sum, but we're doing continuous time, so it's going to be an integral, and chi is going to be the characteristic function of this set C. Okay. So just the ergodic theorem applied to that function. So claim, given a V belonging to this full measure set, we must have a T0. And it's depending on V, but that's okay. So for all T greater than T0, St chi of V is less than S1 plus epsilon T of chi of V. Okay. So I'm going to prove this. Okay, I guess this is a subclaim. I'm proving a claim already. So let's prove this subclaim. So I mean, if this wasn't true, then there exists a sequence tk going to infinity with stk chi v equal stk 1 plus epsilon chi of v, right? And that's going to contradict the ergodic theorem. 1 over 1 plus epsilon, 1 over tk, stk chi v equals 1 over 1 plus epsilon, tk, stk, 1 plus epsilon, chi v, and of course, you know, the thing on the right goes to the measure, and the thing on the left goes to 1 over 1 plus epsilon times the measure. That's a contradiction. Taking limits, 1 over 1 plus epsilon, yeah, measure of C equals measure of C, contradiction. Okay, so that was the proof for the subclaim. So I've got a, if I go far enough along, I've always got a gap like this. But it follows that FTB belongs to C for some T belonging to T 1 plus epsilon T. Right, so you know, what does it mean to have this number bigger than this number? It means exactly that this characteristic function turns on somewhere in the window between T and 1 plus epsilon T, right? In other words, FTV enters the set. And this is, yeah, oops. Yeah, for any t greater than or equal to t0. Okay. So what's that shown? It's shown that for almost every v, there exists a t0, depending on v, so that v belongs to this set B epsilon greater than or equal to t0. But we can carry out the same arguments for each C. Okay. Okay. Okay, and let's say for almost every V belonging to C, because I wanted these things that recur the way I set it up, right? So that gives us a full measure set. Okay. So what does this show? This shows that the Liouville measure of the union of T B epsilon greater than or equal to T equals 1, because I just wrote that way, but yeah, the set here is nothing but Z, right? Every point in Z was in one of these guys. So yeah, the set Z is here, that had measure 1. But I wrote it that way, just, we can observe that, since B epsilon greater than or equal to T is an increasing sequence of sets with T. Just to think about that for a second. This is saying that for a fixed T, you're getting this recurrence starting at T and at every point forward of that. And so I'm saying if you increase that threshold, I've got a bigger set. That's an easier condition to meet, right? So it's a bigger set. So we've got an increasing, an increasing family of sets which exhaust the space. So mu L of union B epsilon greater than or equal to T goes to 1, which is what I wanted. What was my claim? Right. So I actually proved something better than what I wanted. That the greater than or equal there is a stronger thing than not having the equals there. And in particular, mu L union T, the epsilon T goes to 1. Each of those sets is bigger than each of those sets. Okay, so that was the proof of the claim. Good. Yeah, I don't know if people who work in recurrence all the time don't feel the need to write that down and just go, oh, everyone knows that, that's ergodic theory. But I don't know. For me, one had to be a little bit careful about point-wise convergence, and I don't know. I needed to see that. Wasn't obvious to me. Okay. Okay, so does everyone buy that?
Yeah. Could you scroll up to the definition of B epsilon T again?
I can. Good idea.
Okay.
Yep. All right. So that was some preparation work. So epsilon was fixed, and small, I guess, but the conclusion is that, okay. Okay, we conclude that we can intersect these sets for all epsilon, maybe for all small epsilon. What am I doing? Okay. For all epsilon delta greater than 0, small. I can find a t with legal measure, still with G1, A epsilon greater than or equal to t. Don't want the greater thans, maybe. I'll check what that means now. I might have just changed my notation slightly. Hang on. Let me not get into a notation mess. Let me remember what I wrote. Right. Let me change this slightly. That's absolutely no cost. Oh, that's a little irritating. Okay, I think I probably want this to switch on for all big T rather than an exact big T. Of course, that's absolutely no problem whatsoever. See here. Okay, how do I retcon this, as they would say in the comic world? Okay, so, oh, it's easy. Okay. Right, and same story. And I'm just going to throw in a greater than or equal to there. Nothing changed. Okay, excellent. Okay, this is a rabbit hole that really doesn't matter. I'm just trying to get everything to add up correctly. All right, well, either way, okay, yeah, okay. What I'm going to write is going to be true. Maybe I could have just got everything to match up slightly better, but no problem. Let's not get hung up on it. I'm going to get these guys to be greater than 1/2. I'm going to have to find out in a moment whether I really care about these greater than or equals, or I'm just going to do a fixed one, but it's really not going to matter. And just in case I need to do all sufficiently big, that's built into this statement. Okay. Right, so I fix my epsilon and my delta, then picking those t's big enough. You know, both of these families are exhausting the space, so I can find a set with, make sure that the intersection of these has uniformly positive measure. May as well be 1/2. Good. All right, now we're getting somewhere. Okay, so what are epsilon and delta going to be? Epsilon's just going to hang out. Epsilon's going to be a small epsilon. Delta is going to come from the Anosov closing lemma. That if D, B, if TB is less than delta, there exists a closed geodesic. Gamma V of period T prime with the difference between T and T prime less than epsilon, such that B sub T BW less than epsilon, where W is gamma V dot 0, I guess, if I parameterize it that way. Right, so delta is just, i.e. delta is constant coming from an also closing lemma. Say, to close at scale epsilon, right? Okay. So, we want things to be, we take things that come close, and we can close it up, and we move a little bit. So I'm saying that I want the thing I create to be epsilon close to all the data that went in at the start. So I'm making these things come delta close, so that after I close, everything's epsilon close. Right. Okay. So let T be large enough that the mu L at G1 of A epsilon greater than or equal to T intersects at B delta, oops. Greater than 1/2, right? But by the claim here, I just put in the epsilon, the relationship between the epsilon and delta that I needed. That's all I did. Okay. I really like this proof because we're about to use a bunch of things that we've proved already. So let E sub T be a maximal T 3 epsilon separated set for this guy. A epsilon greater than or equal to T intersect B delta greater than or equal to T. Right. A maximal T3 epsilon separated set for this guy. And this guy has definite positive measure, and recall that 1 over T log of the number of points in ET. The growth rate, the exponential growth rate of these things is going to be nothing but our old friend the entropy. And that's by something that we saw some time ago, maybe in lecture 10 or something like that. That's our old friend, the Katok entropy formula, right? Maybe I never wrote it out for flows, but the flow version is just like the discrete version, but with T's instead of N's. It's a really nice characterization of entropy if you're in a compact metric space. If you're in the topological situation, you look at the number of things it takes to cover a set of, or to be separated in a set of uniformly positive measure. That growth rate gives you the entropy, the measure theoretic entropy. Right? So that ties together something nicely that we saw before. And I believe that the first time the Katok entropy formula was written down and proved was actually for this very proof. I think it was discovered in the proof of the result we're doing now. So it appears in Katok's 1980 paper in the publications of the IHES. Of course, it's a generalization of Shannon, Macmillan, Breeman type thing, but this was the first time it was done in this setting. That's why it's called the Katok entropy formula. Okay, so the plot is thickening. We have lots of points capturing the entropy, the Liouville entropy. So this is how this entropy enters the picture. Of course, the only reason we can do this is because these sets have positive measure with respect to this guy. The positive measure sets with respect to Liouville measure, that's why they're seeing Liouville entropy. Okay, so for each V belonging to E sub t. What are we going to do with it? We're going to close it. That's one of the two properties. We're going to close it. That's going to give us a closed geodesic. The closing was from this guy. And okay, so what's happening? We're closing it using that property. We're going to have lots and lots of points such as this, capturing entropy. So that's how that's entering the picture. And of course, we'll see in a moment why this is exactly what we want, how this bracket G1, G2 thing enters. It's probably hard to see where that ingredient is going at this point, but that will be revealed soon. So for each v belonging to E sub t, we obtain a closed geodesic gamma sub v from the anosal closing lemma. So again, there's another result we proved, or at least discussed in detail some time ago. So lots going on here. We've got Katok entropy formula. We've used the Hopf argument. We've used the anosal closing lemma. So really, so many of the tools that we've been building are needed for what we're doing right now. Okay. So let WV be right. Just parameterizing it and notation beyond the geodesic. So let's just pick a point on this geodesic gamma v, the one that has dt v wv less than epsilon. So just parameterizing it. So I had gamma dot v0 earlier, but just slightly different notation. Okay. Then the set of points wv, so v belongs to E sub t, is t epsilon separated. I don't think I'll elaborate on that. Again, this is a kind of lemma that we've seen multiple times. What went in was 3 epsilon separated things. When we went from v to wv, we moved by up to epsilon. So they start at 3 epsilon apart. Each coordinate might collapse a bit, and the things we created are still epsilon apart. Right? Good. So we have lots of points. We always want that. Or we usually want. We often want that. And how many such things did we build? How many closed orbits did we build? It's going to be, I claim it's greater than or equal to. Again, this is an argument that we hinted at when we were looking at periodic orbits for flows. Okay, so we don't have any guarantee that this construction was putting us on geometrically distinct closed geodesics. We have to live with the fact that, okay, there was a closed geodesic. We might have to live with the fact that maybe V1 outputted a point there and V2 outputted a point there, and they're actually on the same geodesic. So we've got to live with that when we're counting the number of like whole orbits that we built. So what we're going to get is an epsilon over t, 1 plus epsilon. I think I need a plus epsilon here. If I'm being overcautious, then it's no big deal. Times size of ET. Right. Okay, so all this is here is that's the smallest between WVs. I mean, all I'm doing is just, this factor is just coming from, what's the worst thing that can happen with, number of things which are packed onto the same geodesic. Well, it's just, they're epsilon separated. So, those two must be epsilon apart. How many of those can I fit on the same orbit? It's epsilon, divided by, what is the worst the period can be, the biggest period. So, this is an upper bound upper bound on the period of gamma, right? So all the things that went in there, so V came back close to itself at a time which the biggest it could have possibly been was t times 1 plus epsilon. Then I closed it. Closing it might have shifted it by an additional epsilon. That's the longest thing I could have possibly created. And so, and then there's epsilon divided by that number, possibly on the same thing. Okay, so that's the worst collapsing I can get of this number, onto same geodesics. So the number of geometrically distinct geodesics is bounded by this. Okay. Okay. Okay, so since mg1 has negative curvature, all these geodesics, so closed geodesics, belong to different free homotopy classes. We'll use that fact soon. Right, this is, I guess, a big fact, but I guess this is kind of general knowledge. So if you're in negative curvature, there's, in each homotopy class, each one of them is indexed by an element of the fundamental group. That there's a unique closed geodesic in there. Okay, so the different geodesics are kind of benchmarked by, by the topology. Right, and for those of you who are into this, if you want a more intuitive explanation, it's really, there's one closed geodesic for each kind of possible journey through the holes, right? Roughly speaking. And that's a negative curvature thing. I mean, if you have non-positive curvature, you can have a flat strip, and that will give you like a ton of closed geodesics in the same homotopy class. Okay, now we're really getting somewhere. Lemma. There exists a constant, k epsilon. It's independent of t and satisfies k epsilon goes to 0 as epsilon goes to 0. I think that's important. We'll find out. So that okay, now we're really getting to it. So that the G2 length, right? We may have lost sight of it in all the details. I'm comparing G1 lengths and G2 lengths. And I'm claiming that the G2 length of of one of these things satisfies L G2 gamma V is less than or equal to T times G1 G2 plus K epsilon. And this is going to be the key thing that makes everything work. Okay. And I think the proof is going to make clear why this is true. But let me just note, what is this thing? It's a closed geodesic, aka periodic orbit, in the metric G sub 1. But if we're looking at it with our G2 goggles on, but with respect to G2, it is a closed curve. Presumably not geodesic. It's just, as far as G2 is concerned, it's just going to be some closed path, right? We can still measure its length, but it's not geodesic anymore. Okay. So closed geodesic in G1, I'm measuring its G2 length. Two different ways of measuring. Okay, so let's estimate proof. Estimate the G2 length of this closed curve? Well, let's just remember what length is. It's going to be the integral 0, just be careful, 0 t prime over n. I'll explain the n in a moment. What is length? Let's just think back to elementary geometry type things. I just take a parameterization. I may as well parameterize it using geodesic flow, G1 geodesic flow. And I'm just integrating the norm of that thing. That's what length is, right? Okay. Let me just explain what's going on there. Here, t prime is the okay, yeah. Here, t prime less than 1 plus epsilon t plus epsilon is the period of gamma. No, okay. Let's be careful. Is a period of gamma. Right, that's all that was really guaranteed. We closed it. There was nothing in that construction, the Nosov closing lemma, which tells you that's the least period. It's very easy to be sloppy with this. A lot of the time it doesn't matter, but there was no reason we got least period there. If you want it to be awkward and come up with an example where you use the closing lemma and don't get a least period, it's easy to do. So all I've got there is that is t prime is a period. Least period is that divided by something, right? Some t prime over n, okay? And the length of a curve of a closed curve is its least period, right? Anyway, that little detail comes out in the wash immediately because I'm upper bounding this guy. So, if it wasn't a least period, who cares? Because I'm upper bounding its length. Right. Okay, so let's split this up into 0 up to t. Definitely got that in there. Plus the change. So what are we going to do with these terms? Okay, these are points WV. So V is the thing we know about. WV is the thing that we shifted a little bit. So this is less than or equal to integral 0 up to t fs g1v g2 ds. Right, that's something we know about. I wanted to replace that term with this term. So the cost is integral 0 up to t. Get the difference between the WVs and the Vs. Plus epsilon t K0. And K0 is just going to be a maximum value on norm G2. Okay, so let's just explain this. This term I've just killed in a crude way. This is the change t up to t. So it's not t1, it's t prime. Right, t prime is at most this number here, 1 plus epsilon t. So 1 plus epsilon t minus t, that's my epsilon t, and I'm just crudely bounding this with a number that's just maximum on that. Okay, so that's killed crudely. Maybe it should be epsilon t plus epsilon. If so, I'm going to absorb that into the K0. Okay. And then here, I've just replaced this term with, instead of a WV, a V. and just a difference between those two things. Okay, so let var epsilon be the biggest difference between size of V and size of W, such that the VW is less than epsilon. Okay, right. So just like var epsilon term is gonna take care of this guy. This is bounded by t times var epsilon because these things are close. And recall that by our setup, this is exactly what went in there in the first place. The average, so this term here, this time average or sum, the way I've written it now, is less than t times g1, g2 plus epsilon, right? That was what we put in then at the beginning. That was the A property, was that these V's were capturing, that their averages were capturing this number. So what have I got? That term gets bounded with this. This term gets bounded by this times t. And I've already got this bit of change here. We obtain G2 length, gamma V less than or equal to T, G1, G2 plus epsilon plus var epsilon. Var epsilon is coming from that second term, plus epsilon K0. So letting K epsilon equal epsilon plus var epsilon plus epsilon K0. We're done with this lemma. Okay. So we've got an upper bound on the G2 length of these G1 geodesics, which are just closed curves from the G2 point of view. Okay, we're getting to the punchline. Okay, I need one more geometry fact. Let gamma be a free homotopy class containing gamma V. Okay, this is another real negative curvature fact. So I already told you that there's a unique closed geodesic in there, but it can be characterized as actually that, this is just classic geometry. The closed geodesic in there can be characterized as the shortest curve in there with respect to G sub 2. So you can think about the homotopy class kind of parameterizing, some journey through some of the holes in your two-hole torus or whatever. And, you could think about, putting a piece of string through that path and tying it up, and then pull it as tight as you possibly can. And, the shortest thing you can possibly make it, well, it achieves the minimum, and that's your closed geodesic, okay? And that's exactly what we're going to do. I've got this curve in this homotopy class, but I'm now going to pull it tight to make it the shortest one, or I'm going to compare it with the shortest one, which I'll denote alpha, which is a closed geodesic with respect to G2. So the shortest thing in the homotopy class is the closed geodesic, the G2. I'm doing distance upper bounds here. So I got the G2 length of, sorry, let's not get sloppy with my handwriting. G2 length of alpha, that's my closed guy in the homotopy class, is upper bounded by the G2 length of gamma V, which is just some closed curve in that homotopy class. And that's the thing that we just bounded. Right? So now we know about G2 closed geodesics. I'm about ready with the punchline. This is going great. Thus, the number of closed geodesics in G2 of length up to T G1 G2 plus K epsilon is greater than or equal to the number of things we just built. This is the thing, right? We're looking at growth rates of periodic orbits up to some length, but you know, the length depends on the metric. So, you know, we built all these gamma V things, but, you know, we had to know how long they were from this point of view. But everything we built has length, you know, up to here with respect to this. And each thing we built here gave us a distinct thing here, or we could compare it with a distinct thing here. Okay. And we've already seen that this guy is greater than or equal to epsilon over T, 1 plus epsilon, I think plus epsilon, just to be cautious. Size of the stuff we put in at the beginning. I want the growth rate of the thing on the left. So 1 over T, G1, G2. Looks like I'm going to overrun by 1 or 2 minutes, but not more than that. Log of right, just normalized by the appropriate time that we're thinking about. Greater or equal to, what have I got? Hang on, I probably haven't had a more efficient way to write this. Okay, good. I'm guessing G1, G2 plus K epsilon minus 1, right? I just divided on this side. So that's coming over to this side as well. And I'll put the 1 over T in the rest. 1 over T log of cardinality ET. Okay, so I took a log of this side and then I divided by all this stuff. So I got that divided by 1 over T. And I've also got 1 over T times log of this business here, which is all just stuff that comes out in the wash. You know, may as well write it out. Log epsilon minus, I don't know. I want to absorb that. That's a little annoying. So I'll use a factor 2. Log T minus 2 log 1 plus epsilon, something like that. Great. Of course, all that stuff over here just goes away. Taking limits. T goes to infinity. What have I got? Oops, we obtain. No, we obtain H star G2, growth rate of periodic orbits with respect to G2 is greater than or equal to, what did this grow like? This grew like the Liouville entropy of G1. That all just got killed. And of course, we're left with this term divided by G1, G2, plus K epsilon. Okay. So it was important that K epsilon, we knew something about it because epsilon was arbitrary. And K epsilon goes to 0. As epsilon goes to 0, we're done. That proves the key lemma. Pretty cool, huh? If there's ever a couple of lectures to study, these are they. I've gone over, but I can't resist writing the conclusion because we've just been doing all this technical work. That was the key lemma. And if you go back to the last class, you'll see that the key lemma gives us, in a short argument, the following statements: variable negative curvature surface, the Liouville entropy G is less than or equal to minus 2 pi Euler characteristic of M over its area, square root, with equality if and only if constant negative curvature. And of course, this number here is just the same as the topological entropy at G0, okay, which is the conformally equivalent and same area constant curvature guy. Pretty cool, huh? And that is one heck of a theorem, a Katok classic from 1980, and with a improved and streamlined proof in 1988. I mostly followed the 1988 version.
What's the title of the paper? For applications, oh, this will be enough to find it. Conformal equivalence in, I think, geometry and dynamics, and it's a paper in ETDS. And it references back to the 1980 paper, which is where these ideas were introduced. Okay, so that is, oh, we've got a link. Excellent, thanks. So yes, that's one half of it. The other half is easier. So the other half is showing that the topological entropy, conversely, is minimized at constant curvature. I think I can do that whole proof on Monday. And then we'll break. I think we'll need a break. I'll need a break. Cool. All right, I'm going to turn off the recording now. See you Monday.
See you.